Hi everybody, it's Mrs. Mancuso and we are starting a new unit. This unit is nuclear chemistry. So all year long we have been talking really about the outside of the atom, the electrons, and how elements bond and form compounds and how compounds can react and change compounds. But now we're really just going to focus on the nucleus and how the nucleus can change. And just like with electrons, it's really about stability. And what happens is that when you do not have a good proton-neutron ratio inside of the nucleus, think of it as like too much force building up in one small space. We know that a nucleus is small and dense, and so if all of these positive protons and all of these neutrons are in this location, sometimes it's just too much, and so they can literally fall apart. So here is a nucleus and it's falling apart. And when it's falling apart, I want you to notice two things. So this is the nucleus that I'm starting with. And you can see that it has 94 protons and it has 240 minus 94 neutrons. And what happens is when it is unstable like this, because it just has so many protons and neutrons in it, it's a very heavy nucleus, it loses a particle. So it emits something. This particle that it's emitting is why it is radioactive. When something is radioactive, it means that it literally the nucleus will break apart. So it loses what's called an alpha particle. We're going to talk about different particles that are lost. This particle has a mass of 4 and 2 protons. So it's equal to the same thing as what helium is. So it essentially loses helium. So it's no longer Pu anymore. It now changes to U. It changes to uranium. And that's because it lost 2. So if it loses 2, it goes down to number 92. And 92 is uranium. So when it does this, this is called decay. And because it lost an alpha, we would call it alpha decay. And this is natural, meaning it happened all by itself. There's only one reactant here. You didn't fire something at it to cause the change. It happened all by itself, again, because it was unstable, that very high proton to neutron ratio inside the nucleus. And it is called a transmutation. So a trans means that it has changed. Well, both the words trans and mutation both mean that they have changed, and they change element. It went from Pu to U. All right, so that is the kind of thing that we're going to be looking at today. So the first thing that I want to go to is the next reference table. Whoops, what's going on here? Okay, so the reference tables that we're going to focus on in this unit are table N, which tells us different radioisotopes. So all of these substances here are all substances that naturally decay. This column tells me the element. This tells me how long it takes to naturally decay. So its half-life is how long it takes for half of the sample to decay. This tells me how it decays. So we saw an alpha decay. This one is B minus. I'll tell you what that means in a minute. And its name, so gold 198. So AU with a 198 up there is the same thing as saying gold 198. Okay, so now let's look at these decay modes, these particles. Over here in table O, it tells me different symbols that are used in nuclear chemistry. So I'm going to look for this B minus, and there it is. So this is called a beta particle. You could write it as 0 and minus 1e, or you can put the beta sign, 0 minus 1b. Whereas in alpha, when something lost an alpha, it lost a mass of 4 and it lost 2 protons. So that's the same thing as helium, or 4, 2, and you can draw the little alpha. All right, there are others. Here's another one. B plus is a positron. So here's positron. 0 plus 1e, or you can put the positive b for a positron. So basically it's like the positive value of a beta. All right, a gamma is like what you see in an X-ray. It's extremely penetrating, has a lot of power to it, but it has no mass and no protons. A neutron and a proton you already know. So a neutron has a mass of 1, but no protons to it. And we just call those N's. And a proton is a mass of 1 and 1 proton. So 1, 1, and it's a P. All right, writing decay reactions. Okay, so when you write a decay reaction, let's just pick any one of these. So I'm going to pick this one right here, very randomly, 220 FR. So I write 220 FR. And now I need my reference table because I need to be able to look up what element FR is. So I'm just literally grabbing my reference table at the same time here. Okay, FR, where are you? 87. Then draw an arrow, because remember, there's only one thing before the arrow in a natural decay. And then look again at what happens to it. It does alpha. Alpha is 4,2He. Okay, so I know it's going to have this come out of its nucleus. So what I have to figure out is what does it transmutate into? What does it change into? So 220, 4 plus 216 would equal 220, because I always have to balance everything. So that's what this would be. And 2 and 85 would give me 87. So this would fall apart into these two things. Now I go look up element 85 on the periodic table, and it's AT. So it became a slightly more stable molecule by changing into this element instead of this element. Let's do another one. All right, let's do this one. 137 CS, and it does B minus. Okay, 137 CS. Now I got to go look up what element CS is, and it's 55. I want a B minus over here. I want it to be beta decay. So I look up what a B minus is, and it's 0 minus 1E. Okay, 0. So it lost no mass. So it still weighs 137 atomic mass units. I need this and this to add up to 55. So this would have to be 56. 56 minus 1 would give me 55. So the element changed to barium, Ba. And so that's all you do for natural transmutation. So in the work that I have you do for week 1, you're going to pick 6 different ones, not the ones that I did, but 6 different ones and do them. Let me do a positron one. So I have one of those listed for you. A B plus, here we go. 53 Fe does B plus. Okay, Fe is iron, it's number 26. It does the B plus, so 0 plus 1E. Okay, so this is 0, so this would still be 53. And 25 plus 1 would give me 26. So element 25, it changed to manganese. There we go. So that's how you do the natural transmutation reactions. It's how you write the decay reactions. And remember, you're just showing how it falls apart. How does the nucleus change into a different element? All right, relative particle strength and charge. Okay, so the most common particles, we're going to talk about alpha, beta, and positron. We are also going to talk about gamma. All right. Alpha is positive charge. It has a mass of 4 and it has 2 protons, so it's just like helium. So this is actually easiest to block. It is the slowest particle because it is heavy. So having a mass of 4 makes it very heavy. You can actually stop this with a piece of paper. It's easy to block an alpha radiation. Beta is minus, so it's 0 minus 1e. So we'll say this is like a medium one. You need a little bit more to block it. It doesn't have mass, so it travels a little easier. A positron is positive 0 plus 1e. So we'll also say this is sort of a medium one. But gamma has no charge, no mass. So it has like a little symbol like this. No mass, no charge. This is the most penetrating. This is the fastest. This is like X-rays. This can go right through. To block it, you need something like lead, PB. So think about, when you think about gamma, think about what you wear to block an X-ray. So like if you have an X-ray, you only want the X-ray to penetrate that one area of tissue in your body. You don't want it to go throughout your body. So you wear that heavy lead blanket to block it. Now, the reason why I'm showing you this is because there's a really common question where it will show a field, and let's say these are all positive on this side and all negative on this side, and you fire something through here. If whatever you're firing goes up towards this, it must be negative because it likes the positive. So the only negative one that we had was beta. And if it goes this way and it likes the negatives, it's got to be positive. So the positive ones that we talked about were alpha and positron. And then if it goes right through and it's unaffected by either one, it has no charge. So that was gamma. All right. And that is the end of it. So I just want to talk about something for a minute. I am breaking nuclear chemistry into 3 parts. So today we just did part 1, which was what are the different particles that an element can, or that an element, but an element's nucleus can lose, and how do you write out their decay reactions. So that's week 1, and that's all going to be posted. Week 2 is going to be half-lives. And I know you've probably done half-life problems before. So this is all calculating, like, hey, if one half-life has gone by and you started with 100 grams, how much is left? And then the third week is doing artificial transmutations. So things like fission and fusion. And that brings us to the end of chemistry. So I'm actually going to work on video 2 next, and then I'll post it, and video 3 next and post it. And I already worked on the little worksheets that you do following each one. So I will post everything so that you choose your pacing. If you're like, hey, I would like to get done with all of this work right now, go for it. Watch all 3, do all 3 work packets, and finish up chemistry. If you have questions, as always, please just message me, and I am available for Zooms on Fridays at 1. If you would like to do a one-on-one Zoom because you're a little bit behind or you have something that you have questions about, just message me and we will review. Thanks. Have a great day, everybody. Bye.